per CEP. So this picture illustrates a typical CEP application architecture irrespective of the platform that we saw on the previous slide. The event sources are responsible for producing sending the events. The source should be publishing events like tickers, or in some event sources it could be a pull mechanism or a push mechanism, like we can get this data from the database, or there is some queue on which the tickers or the feeds pricing systems are publishing their data over on those queue, and we are getting that data from those queues or messaging architecture. Within CEP engine, there would be some amount of pre-processing required, like converting the source specific event format into CEP specific understandable format. Once the pre-processing is done, the events are then washed over the queries that have been predefined. A matching pattern thus found in the within the CEP queries that is captured, it would be interpreted as a complex event and forwarded to the post-processing. In post-processing, you can imagine it as a reverse process of pre-processing, where CEP specific format is undone and the sync target specific format is created. The event could be made available to target as a push or a pull. So in this case study, the event type of interest is the market data event. This event could be represented as a POJO or a POCO, depending on whether we are using Java or C#. In Java, you could use any of the following constructs. You could use object, map, object array, or a node. It is important to note that these type of events are supported in Esper. Similarly, other CEP engines may offer varying degree of support. The stream could be market data feed that is taking from the market data. The first step of applying a pattern would be to group the relevant events. These grouped events are basically based on the windowing. So these events are correlated using a common set of technique called windowing policies. There are temporal windows and spatial windows. Temporal windows can be used to do a stateful event correlation based on event occurrence. A peephole is created in event stream based on the time in which state of the previous event in the stream is used with the current event state to determine a pattern. So spatial correlation or dimension based window are similar to the temporal window, except that the peephole is the number of events based rather than the time based. They are also called count windows, as the count of the event determines the window. Direct filters that can be applied on the attribute of the window are called aggregated events. So when all tuples are evicted from the existing window before a new window is created, window is called tumbling window. When only the oldest tuples get evicted so that the window condition is met, then the type of window is called a sliding window. So to illustrate the window and sliding window, consider the following input. There is a series of data that is coming in 1, 2, 3, 4 up to 13 or infinite. So our stream can be infinite, and if we look like a tumbling window, it is defined as a length of 3. So it will take first 3 elements, keep them, and when the 4th element arrives, all the first three events, they are evicted from this window, and it will wait until 4, 5, and 6 event come. 4, 5, 6 would be allowed to sit over there. When the 7th event comes, 4, 5, 6 are moved. And likewise, this tumbling window continues. It is also called batch window. In Esper terms, it is called batch window. If we look at the sliding window is something, if I define a window of length 3, then it will have only 3 elements, but the oldest element every time will be removed from the window. So when 4 comes in, 1 would be evicted, 5 comes in, 2 would be evicted, and likewise. So some of the more pattern matching techniques are based on filtering. Filters can be used for specific query selection of events or projection. Selection happens based on the event attributes. These are called direct filters. They can be used to narrow down the result for further processing. For example, like where clause will let us only those events that satisfy a particular condition to flow through further into the pipeline. Filters can also be used to eliminate unnecessary attributes. For example, those attributes that are not used in further computation can be removed through filters. I can write a simple query that select only bid size, bid price, bid size, quote time, and stock, and obviously the ticker symbol. Only these information I want out of the market data. So I can create another event from the incoming event to the event that I am interested in. So that is called projection. Grouping of events can also be done. So we can also do grouping. Grouping can be done using group by expression. This is very similar to the SQL approach. As an example, like I have written a query, select last close from the market data, group by ticker symbol. So this will group the last close price by ticker symbol. So as the events are correlated, aggregates should be calculated on these events for further computation or filtering. To calculate the events, events should be grouped into a set. Grouping events can be achieved over by windowing, as we discussed earlier. Partitioning, the window partitioning techniques can be used, as we discussed earlier. Aggregates can be calculated on any type of the window defined, like a temporal window or a tumbling window. So you can also see like example over here where we are calculating the average over a period of 1 hour for the price. So some of the CEP platforms have built-in aggregate functions such as sum, average, min, max, count. Some platforms allow running statistical calculations like standard deviation, median, variance, and support retrieving values from the windows like first, last, first n elements, last n elements, for writing aggregate expressions on the window. These platform also offer extension points so that the user can create his own aggregate functions that can be written into some external languages like Java, C#, or C++. Joins are way to merge two streams to one stream by applying intelligence. In our case, as noted before, we shall be having two streams. In fact, not two, but we will have actually 4 streams. 3 will be for exponential moving average, 1 would be for Japanese candlestick data, and the other one would be market data itself. So we will be using all these streams to get a meaningful event for us, or the condition that we want to reach. So just as an example, here what we are doing is that if the market data is below the EMA 5, just as an example, in that case, and the market data ticker symbol is also same as that of the EMA ticker symbol, then you want to select that particular event. Okay, so with that, let's discuss about the Esper. Esper is an stream processing, event stream processing and event correlation engine. It is targeted to real-time event-driven architecture. Esper is capable of triggering custom actions written as plain old Java when event conditions occur among event streams. It is designed for high volume event correlation where millions of events coming in would make it impossible to store them all and query later. Esper also comes up with a tailored event processing language called EPL that allows expressing rich event conditions, correlation possibly spanning time windows, thus minimizing the development effort required to set up a system that can react to complex situations. Input and output adapters to Esper provide means of accepting events from various sources and for making available events to the destination. Most adapters present in their own configuration, as well as there is an API that comes with Esper. Esper as a whole is written in lightweight kernel which is written in Java and is fully embeddable into any other Java process. So Esper also provides adapters to connect with the databases and retrieve historical data from there. While it gives a rich event processing language which comes up with the query language as well as pattern recognition language and attaches the temporal nature to it, Esper provides windows as well. So there is a lot of work it is doing in memory, and the best part is that it has got a very high throughput, and number is quite high. I should give you the number. It is around 10,000 to 200,000 events per second. Isn't it something really great? So let's jump directly into the implementation part. So if I want to send any event to Esper, I would require to get access to its runtime. So if I look at this particular class, which is called EP service provider, that provides me access to the runtime as well as EP administrator. So what this administrator interface is, this interface actually includes methods like create patterns and create EPL statements. So administrator gives us power to create queries and create the patterns, whereas EP runtime that provides methods like send event, and it also accepts timer callbacks for synchronizing timer events with the regular intervals sent in. So I'll move to the demo, but let's move to a couple of slides more, then we'll directly move to the demo part. So obviously, like the continuous query, the cycle example, if you remember, continuous query is very important for Esper, and whatever queries we will see in our demo, we will see that those are continuous queries. Combination of select, filter, grouping, aggregation, and join. We have already seen what these aggregation are, what filters are, and we will see more in our code. So here is one example where I am sending an event. I have already sent an event, and there is a query, select average price from quote window over a period of 30 seconds. This is an expression, and this is the administrator. The third statement is the EP administrator, which will create EPL. The interesting part over here is the update listener. This is an interface which provides a method called update and is invoked by the Esper engine whenever there is a change in the statement's result set. So whenever I want to post any result set to the listener, I will use this particular listener to do that particular work for me. So all I have to do is just create a listener and attach that listener to the statement. So here we have come to our demo section. I'm just moving to the demo. First I'll show you the code and then we will do a demo. The class that we are seeing currently is a market data class, which has all the attributes that we discussed about the market data, like ticker symbol, bid size, ask size, last sale, exchange, and volume. All that data that we intended is over here. There is a tool which is a benchmarking tool called FinCos. So in our case, like although it is a benchmarking tool, but what we are doing is we are creating load for ourselves. Let me show you. So this particular FinCos tool, it will send us this data that which is a market data event, and it has the same things like ticker symbol, bid, price, and exchange, whatever we discussed. This will send us over a Hornet queue. So it will send us over a Hornet queue, and from the Hornet queue we have a listener. FinCos service. FinCos service basically registers a listener and it converts all the attributes that are coming from the FinCos and it sends over to the stop loss engine. Stop loss engine. So as soon as the stop loss engine receives the market data, it sends that data to the Esper engine. So if you look at this statement, line number 63, it is sending that data to the Esper engine. So there are some queries that we have written. I'll show you those queries. So first query is insert the market data into quotes window. So here is a quote window where we for every market tick that is coming, we are inserting that into a quote window, and that quote window only holds the event for only one event. But when we want to create our Japanese candlestick that we discussed earlier, so Japanese candlestick would be created over a period of 5 seconds. So let's see this query which inserts a Japanese candlestick. This particular statement is which will help us form a Japanese candlestick. So we are accumulating our data over a period of 5 seconds in a batching window. In a batch window or a tumbling window that we describe, we will take first 5 events, do our analysis over that first 5 events, create our candlestick, and then we will switch to next 5 events. And from those events, first 5 events, we will take these, we will call these aggregate functions, which is called first of the events. So I'll get the first bid size. Max is the max of the bid size, and we call it as high. First is the open, max is the high, min is the low, and last is the quote size. So with that, like, our Japanese candlestick would be formed every 5 seconds. Now from the candlestick we want to calculate our exponential moving average. So if you remember the exponential moving average formula that we discussed earlier, it was the current price multiplied by a factor K plus 1 minus K times the EMA of yesterday. So if you look at this statement EMA 5 window selection, so this statement is particularly the same. It's the same constant that we discussed. 2 divided by n plus 1. We are calculating a 5-day moving average. So it is 2 divided by 5 plus 1, which is 2 by 6. And this is 1 minus 2 by 6, which is 4 by 6. So likewise, EMA 10 and EMA 25 are calculated. And every statement can be given a name, like calculate exponential moving average over period of 25 seconds. Selecting is another statement. And we will also see that with each statement, which are the select statement, we will also add an update listener. And the last statement is nothing but the selection of our buy sell signal. In our case, it is a stop loss signal. So this statement is naturally like we are selecting exponential moving average at that particular point in time. What were the 3 EMAs and the market bid size, which we will be plotting in our graph. And if we look at this query, it says that the market data's bid size is less than the EMA 5, EMA 10 and EMA 25. And it generates the snapshot every 1 second. We can also modify it to generate snapshot every 5 seconds or 10 seconds, whatever we want to configure our engine, right? Let's go back to the stop loss engine. So over the stop loss engine, let me show you the statements. So if you look at these statements, these are all the Esper statements. Select statements where we want to attach a update listener, EMA 5, EMA 10, EMA 25, and here we are attaching the listeners. If I go to the individual listeners, so all these listeners are doing are they are logging the values and also sending those to the chart, which we will draw when we are going to do the demo. So let's go back to our FinCos tool and start sending our load. Okay, so here we see that data is streaming in real time. After first 5 seconds, we see that one candlestick is generated. As soon as first candlestick is generated, we have 5-day data available, and therefore we got our signal of EMA 5 started generating, which needed previous 5-day data to come up. Similarly, EMA 10 would require last 10-day data, and it has come up after 2 candlesticks. And EMA 25 data has come up after 5 candlesticks have generated, because we need 5-day or last 25 seconds or 25-day data. So in our case, we are talking about seconds, so it will be last 25-second data. Now if you look, whenever our market is falling below the 3 moving averages, sell signal is being generated. So I have marked it with the sky blue triangle. At every data point where you see these marks coming up, these are actually the sell signals. Okay, so if we see market as a whole is falling and our market data or the bid size is always lower than the 3 exponential moving averages. So It's generating a sell signal in this case. It's all random data that is coming in. And let's look like it seems that market is going to go up. No, it's just a low. And it is still plotting the signals. And yeah, here the market data goes up and we don't have any more sell signals. The stop loss is over. Okay, with that, let's switch back.